Hello, students. This is Mr. Allen, and today we're going to finish up Chapter 8, finally, Section 8.10. We've spent a lot of time, 10 weeks, in this unit, and we're going to finish things up. We're going to look at Taylor and Maclaurin series. Our first objective is to find a Taylor or Maclaurin series for a function, which we've already done a little bit of that in this chapter. We want to be able to find a binomial series. And we'll just take a quick look at some of the basic lists of Taylor series to find other Taylor series. So our first, let me move this out of the way. So our first theorem here says, this is called the form of a convergent power series. So if we've got a power series, my marker going here, there we go. So if I know my function f of x is equivalent to a power series, for all x on some open interval, then a sub n is equal to the nth derivative of the function at c over n factorial. Thus, f of x can be written as f of c plus f prime of c times the quantity x minus c plus the second derivative at c divided by 2 factorial parenthesis x minus c. We already know this formula. So this is how we get a convergent power series. The coefficients of the power series in this theorem are precisely the coefficients of the Taylor polynomial for f at c. So when we look back at section 8.7 with Taylor polynomials, we can see now we can build these into not just Taylor polynomials, but Taylor series, because these go on for an infinity. So the definition of a Taylor or Maclaurin series is as follows. It is the summation of the nth derivative at some value c over n factorial times the quantity x minus c to the nth power. In an expanded form, we have that here to the right. This is called the Taylor series of the function f at c. If c is 0, it's a Maclaurin series. So in this first example, we're going to form a power series for the function sine of x. We're going to go ahead and make this a Maclaurin series, so we're going to have our center be at 0. So our definition tells us that we just need to do the summation from n starting at 0 to infinity, the nth derivative at 0 over n factorial times x to the n, which is going to give us the following in expanded form. And we also want to determine the interval of convergence. So first, we know that f of x is equal to sine of x. So f of 0 is sine of 0, which is 0. F prime of x is cosine of x. So f prime of 0 is 1. F double prime of x is negative sine x, which is f double prime of 0, which is 0. And then, and I'm going to move my recording thing here out of the way if I can. Maybe I can't do it with my mouse. The third derivative of f of x is negative cosine of x, which yields negative 1. The fourth derivative is again sine of x, so now we're starting this cycle, and this is going to keep repeating, and so on. So the power series is as follows. F of 0 plus f prime of 0 at x plus f double prime of 0 over 2 factorial at x squared plus f third derivative at 0 over 3 factorial x to the third, etc. And now we can just start plugging in our values. We found that f of 0 was 0, f of 1 was 1. I'm sorry, f prime of 0 was 1, f double prime of 0 was 0, and on down the line. And so this can be simplified to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. That can be rewritten in compact form. Notice that we have an alternating series here, so it would be the summation from n equals 0 to infinity of negative 1 to the n, and we're doing odd powers, so that's going to be x to the 2n plus 1, and we're also doing odd factorial, so that's 2n plus 1 factorial on the denominator. By the ratio test, we can conclude that this particular series is convergent for all x. To me, that's just miraculous. It does not matter what x is. You can use this particular series, this Maclaurin series, to approximate any value of x that you want. You cannot conclude that the power series converges to the sine of x for all x. Now let me go back here and look at this again. By the ratio test, you can conclude that this series converges for all x. You cannot conclude that the power series converges to sine of x for all x. You can simply conclude that the power series converges to some function, but you're not sure what that function is. This is a subtle but important difference when dealing with Taylor and Maclaurin series. To persuade yourself that this series might converge to a function other than f, remember that the derivatives are being evaluated at a single point. It can easily happen that another function will agree with the values of f, the nth derivative of f at x equals c, and disagree on other x values. If you formed a power series for the function shown in figure 8.24, you would attain the same series as in example 1. So look at this function here. This is a piecewise defined function. You know that this series converges for all x, and yet it is obvious it cannot converge both to f of x and sine of x. So these are different things. So let me go back to this previous slide. You can conclude that the power series converges to some function, but you're not sure what that function is. Let f have derivatives of all orders in an open interval I centered at c. The Taylor series for f may fail to converge for some x in the interval, or even if it is convergent, it may fail to have f of x as its sum. Nevertheless, theorem 819 tells us that for each n, f of x equals f of c plus f prime of c, x to the nth derivative. The remainder is going to be the n plus 1 derivative at some value z over n plus 1 factorial times the quantity x minus c to the n plus 1 power. Note that this remainder formula is particularly value of z that makes the remainder formula true depends on the values of x and n. If the remainder goes to 0, then the next theorem tells us that the Taylor series for f actually converges to f of x for all x and I. So here's our second theorem. This is the convergence theorem for Taylor series. If the remainder of the series goes to infinity, if the remainder as n goes to infinity is equal to 0 for all x in the interval, then the Taylor series converges to f of x for those values. Okay, so what this is saying is if the remainder is going to go to 0, then the Taylor series converges and is equal to f of x. So this is the stronger statement than what we had before. So here we can conclude, if this is true, that this series is going to be indeed equal to f of x. So let's show that the Maclaurin series for f of x equals sine of x converges to sine of x for all x. So what we need to do is we need to show that sine of x, which is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, etc., here's our general term, is true for all x. So what we need to look at is the n plus 1 derivative. Well, the n plus 1 derivative is equal to plus or minus sine x, which is the same thing as plus or minus cosine x. In other words, it has to be less than or equal to 1 for any real number z. Therefore, for any fixed x, you can apply Taylor's theorem 8.9 to conclude that 0 is less than the absolute value of the remainder, which is defined here, which has to, now what we can do is we can substitute 1 in for this. We get the following. The absolute value of x to the n plus 1 over n plus 1 factorial. From the discussion regarding the relative rates of convergence of exponential and factorial sequences, it follows that for a fixed x, this limit is equal to 0, which shows us that the remainder is 0. And by the squeeze theorem, it follows that the remainder does go to 0, as n goes to infinity. So by theorem 8.23, the Maclaurin series for sine of x converges to sine of x for all x. In other words, the first example that I said actually does converge for all x to sine of x. Figure 825, that's what we got below here. I'm going to move my picture here again. Visually illustrates the convergence of the Maclaurin series for sine of x by comparing the graph of P1, P2, P3, P5 to the graph of the sine function. Notice that as the degree of the polynomial increases, its graph becomes more closely resembles that of the sine function. We've already done this in class when we looked at section 8.7. So guidelines for finding a Taylor series. You want to differentiate your function several times. You want to find the function itself at C, then f prime of C, etc. Hopefully you'll see a pattern. 2, use the sequence developed in step 1 to form the Taylor coefficients a sub n equals the nth derivative at C over n factorial, and to determine the interval of the convergence of the resulting power series. Within this interval of convergence, determine whether the series converges to f of x. Okay, so now we're going to start moving towards the binomial series. And then at the very end, I'll give you a list of some of the basic Taylor series. So binomial is something like the term 1 plus x to the k. So binomial just means two terms added together. So in this case, it's 1 plus x is the binomial. And we're taking powers of it. To find the Maclaurin series for this, that's what we're going to do here in example 3. We're going to just let f of x equals the quantity 1 plus x raised to the k. We're going to determine its radius of convergence. We will assume that k is not a positive integer and k is not equal to 0. By successive differentiation, you will find that, first of all, f of x equals 1 plus x to the k. Well, f of 0 would be indeed 1, because 1 plus 0 to the k is going to be 1. The first derivative would be, now we're going to take k, the exponent, we're going to minus 1 from that, but don't forget we got to multiply by k in the front. We're still going to get 1 for the parenthesis, but that k is in the front, so you have 1 times k, so it's just k. The second derivative is going to give us k times k minus 1. The third derivative is going to give us k times k minus 1 times k minus 2. I hope this sounds familiar. And so on. So it turns out that we're basically dealing with this whole idea of this factorial notation again. So this is going to produce the following series. Again, if we went back to this first one, remember, f of 0 was 1. So that's where the 1 is. F prime of 0 was k. F double prime of 0 was k times k minus 1 over 2, etc. So by the ratio test, we can conclude that the radius of convergence here is r equals 1. I'll leave that for you to investigate. So the series converges for some function in the interval from -1 to 1. And now finally, we'll end this presentation with a list of common power series. So for example, 1 over x is given here. Notice that on the left is the function. So here's our function 1 over x. Here is the expanded form. Here's the nth term. Here's the interval of convergence. Here we have 1 over 1 plus x. That should look very familiar. That should look a little bit like our geometric series. Here's our natural log. We did that as an example. Actually, we did that as an exercise, I think. We did this one as example. We looked at the sine of x. Here is the Maclaurin series for that, which we could easily change to a Taylor. Here's our nth term. We figured out that the radius of or interval of convergence is negative infinity to infinity. Turns out that cosine is very similar, but it's the even powers. Here's arc tan, arc sine, And then this very last one, here's that binomial. Here's that binomial. Okay, final example here. So what we're going to do here is we're going to use that list to figure out the power series for this function, which is the cosine of the square root of x. Sorry about the bell. We know that the power series for the cosine of x is 1 minus x squared over 2 factorial, etc. Those are those even powers I just mentioned, and notice this is alternating. Now what we got to do is we're just going to replace x with the square root of x. So all I'm now doing is instead of x squared, I'm going to do the square root of x squared, which is just x. And then to the fourth, that's going to be x squared. And to the sixth, that's going to be x to the third. And we can go ahead then, this series is going to converge for all x in the domain of the cosine of the square root of x, and that is for all x greater than or equal to 0. Remember, we're dealing with square roots, so we need to make sure that those square roots stay positive. And guys, that's the last example, and we ran out of time there. I almost got done before the end of the bell. Have a good day.